In NTU method, temperatures are unknown, but we can see other values. In NTU method, we need graph. That graph connects effectiveness of heat exchanger NTU C minimum by C maximum. C means capacity rate. In this question, we can see the given data like mass flow rate of hot fluid mh dot. It is given in kilogram per minute, but in all our calculations we need to use SI unit. So we can convert kilogram per minute into kilogram per second. We know that 1 minute is equal to 60 seconds. So 4.2 divided by 60 will give us 0.07 kilogram per second. Next, specific heat of hot fluid. We can replace kilo as 10 power 3. So 3.5 into 10 power 3 joule per kilogram Kelvin. Okay, next, temperature of temperature of cold water. T1 is equal to 15 degrees centigrade. Its mass flow rate is 17 kilogram per minute. It can be 17 by 60, that is 0.28 kilogram per second. Overall heat transfer coefficient 1100 watt per meter square Kelvin. Try to use capital W. Capital W. Area is 0.3 meter square. Okay, these are the unknowns. Outlet temperature of liquid, outlet temperature of water, effectiveness of heat exchanger. Okay, first we can find capacity rate of hot fluid. C or CH. CH is equal to mh dot times CPH. We can get the value in terms of watt per Kelvin. 245 watt per Kelvin. Capacity rate of water Cc. This is cold liquid. So Cc is equal to mc dot Cpc. If water specific heat is not given, you need to assume, try to remember this value. Usually they will give, if it is not given, for water you need to assume. So C or Cc is equal to 1170.4 watt per Kelvin. If you compare CH or C is equal to 245 with Cc is equal to 1170.4. CH hot fluid capacity rate is the lowest value. So this is C minimum, this is C maximum. Okay, we can find C minimum by C maximum. The ratio is 0.209. 0.209. We can find the NTU also. From data book, we can find this equation. We can substitute U value, area, and the C minimum. We can get this value. In data book, we can see this graph. NTU effectiveness versus NTU for all C minimum by C max conditions. Our NTU value is 1.34. Our C minimum by C maximum value is 0.209. So we can consider this curve. We can't see the exact curve, 0.209 curve, but we can see some closest value. So we can choose that C minimum by C max ratio. We can draw one vertical line from x-axis till this line meet the curve, desired curve. From the intersection point, we can draw perpendicular line to y-axis. This is your effectiveness, 64 percentage. 64 percentage, or we can say 0.64. So we got now effectiveness. Next we need to find outlet temperature of liquid and water. Maximum possible heat transfer formula is T minimum times T1 hot fluid inlet temperature T1 inlet temperature of cooling water. So here parallel flow is there. So C minimum times T1 minus T1. This is Q max equation. Actual heat transfer rate Q is equal to Q max times effectiveness. Next we need to use the general equation in terms of hot and cold fluid temperatures. Q is equal to mc dot cpc times T2 minus T1. Except T2, we know other values. So this equation will give us T2 value, cold fluid outlet temperature. Similarly, we can use Q is equal to mh dot cph T1 minus T2. Here T2 is unknown. By equating the terms on left and right, we can find the unknown T2. Okay. In this type of NTU problem, we will be asked to find effectiveness, temperature, and heat transfer. So we can use graph. In the graph, we can see some common terms like C minimum by C max, NTU, effectiveness. From NTU to C minimum by C max curve, we can draw one vertical line from x-axis. From the intersection point, we can draw vertical line to y-axis. Okay. At the beginning, I written some equations, two equations in terms of hot and cold fluid inlet temperature conditions and exit temperature conditions. So from these equations, we can get cold fluid outlet temperature and hot fluid outlet temperature. Okay. Yes. Try to practice many problems